Okay, so I'll start with a few definitions. Yes, Joanne. Yeah, I didn't bring one today, so we just miss it. Okay, radicals and rational exponents. So by rational exponents, what I mean there are fractions as exponents. You know, we've dealt with integers, positive and negative integers, so far, and it turns out that all the rules that you learn for integers work for all real numbers or all rational numbers. All right, so let's go through a couple definitions. Okay, so let's say a and b are real numbers, and n is an integer greater than 2, okay, or equal to 2. What we're going to call this, if we have a equals b to the n, then b is the nth root of a. Okay, so here we're defining it not by having some sort of radical expression or anything like that. This is, you know, examine that and you say b is the nth root of a. So if we pop in some numbers there, maybe this is an easier way to do this. If we say, for instance, 9 equals 3 squared, right? This would be n, there's b, and there's a. We're saying that 3 is the second root of a. Okay, that's just from terminology. Now, we don't really talk about the second root, we talk about the square root, and that's because when you multiply lengths and widths, you get square measures, and so there's this very close kind of relationship between squaring something and bringing it to the second power, okay? Similarly, mostly for geometric reasons, when n is 3, we call that the cube root. So if we have something like this, where we have 27 equals 3 cubed, that's probably not the best example because I have 3 twice. Let's talk about 8 equals 2 to the third power. You say 2 is the cube root of 8. Now, notice that there's, in this kind of an expression, we can talk about this, when we have negative 3 squared, that will equal 9. So by the definition I just gave you, we have negative 3 as the square root of 9. And that's generally not what we're talking about, though. So we have this notion now that we're going to deal with called the principal nth root of a number. And so we're just making a rule for what the principal root is. And so we're going to call this thing here in the radical sign, you see the little n up there, that's going to be the index. A is the radicand, and it's not really that important that you know these names. I mean, you know, we know generally, you know, n in this equation is the exponent. In the radical, n is the index, a is the radicand. And so we're making the definition that says the principal of the nth root is that the nth root of a has the same sign as a. Okay, so when we're talking about also square roots, since we deal with square roots so frequently, we don't need the 2 here. It's not wrong if you put it there. Certainly everybody would understand that that is the square root, but we generally just write it with the radical symbol by itself without an index. And that suggests that the index is 2. Okay, so let's look at some examples here. So the square root of 36 is 6. I think you've seen that one before. No surprise there. The cube root of 8 is 2. And now we have the cube root of negative 27 is negative 3. Notice by my definition that the cube root of a number has the same sign as the number. So if a is negative 27, the cube root of negative 27 is negative 3. But this is only going to work in certain cases because we can't take the square root of a negative number. What we get is a complex number or an imaginary number. And really there's no way that you can find a number that multiplied by itself gives you a negative number. So here this really only applies to negative numbers, that you have one principal root of a negative, cube root of a negative number, you get a negative number. We can only take the square root of positive numbers, and going back to this example, we would always call the, if this was A, we would always call A the square root of 9. We would only refer to the principal square root, which is 3, not negative 3. Okay, so let's look at a couple properties of the nth roots. So if A is positive and n is even, we do have two roots, but we're going to refer to this one as the principal root. And if we want the other root, we're going to have to put a negative sign out in front of it to get it negative. So when we go the other way around, we still get 5 squared is 25, and negative 5 squared is 25 as well. If A is negative and n is even, we don't have a real root for it. So we don't take the square root of negative numbers, because nothing times itself will give you a negative number. Okay, and if A is any number now, and n is odd, it has exactly one root. So we saw that with, here I have two examples. The cube root of 8 is 2, the cube root of negative 8 is negative 2. Okay, so now we're going to look at something called the inverse property here. If we take the nth root of A and then take it to the nth power, we'll get A back. And so, for example, if I take the cube root of 27 and cube it, I will get 27 back, right? Because I take the cube root of 27, which is 3, and then 3 cubed is 27. Now, if n is odd, this works the other way too. So if we're going to take the nth root of a to the n, we're going to get a. So we'll do an example here where when we have 2 cubed is 8, and then the cube root of 8 is 2. If we start with a negative number, negative 2 cubed is negative 8, and of course then the cube root of negative 8 is negative 2. So we retain the sign. You see how a here is negative 2 and a is negative 2, ultimately what we get. Now, if it's even, we have something entirely different. Okay, so when we take the nth root of a to the n, we get the absolute value of a. And this is going to be something important to remember when we simplify, that we indicate things with the absolute value and not just write the number. So for example, 3 squared is 9, square root of 9 is 3. If I take negative 3 squared, that's 9, and the square root of 9 is 3. So here, a can be either 3 or negative 3, and I get the absolute value of those, so it's just 3. So notice I never actually use the absolute value sign, but when if this is a variable in here, then I have to write the absolute value sign. For example, when you're writing this, that's not x, okay? What this equals is the absolute value of x. Okay, so let's relate this to exponents again. Okay, so if a is a real number, if we take 1 over n, we'll get the nth root of a. So this is going to be the chief device that you're going to use to simplify radicals, is you're going to put them into a rational exponential form, and then we have all the rules of exponents that we can use to simplify. So 8 to the 1/3 is the same thing as the cube root of 8, which is 2. Is that inside here?
What?
Was that inside? Is that outside? Is my car somebody breaking into or something like that?
Yeah.
Right. Okay, so now remember this property here where if we take a to the m to the n, we multiply the m and the n, and so if we have a to the n to the m, that would equal that as well. So it doesn't really matter what order we put these things in, we get the same product in the exponent here. So just to show you that with some numbers, how that works. And of course, when we get all that, we get 64 equals 64, equals 64. Now with radicals, or with rational expressions, this also works as well. So if we have a to the n over m, like this, we can factor out the n, and then that a to the 1 over m is the mth root of a to the nth power. Okay, so how does this play out? We can do it the other way as well. You see here what I'm doing is I'm putting the 1 over m on the outside and the n on the inside. So here I have a to the m, n to the mth root, and here I take the root first and then take it to the power. Now this is going to be really important when you're simplifying numbers, because what you do is you can take the, just like in when I was talking about doing the scientific notation problem, you know, where we're doing the division before we do the multiplication to make it easier, it's going to be easier for you to take the root before taking it to the exponent. We'll see some examples of that. So for example, just a real quick example, if we have 9 to the 3/2, we can take 9 cubed and then take the square root of that, or we can take the square root of 9 and then cube it. Well, the square root of 9 is 3, 3 cubed is 27, so it's 27. I don't know that I could do it the other way in my head. 9 cubed is what? I don't even know what that is. I mean, you know, I'd have to think about it carefully, and then heaven forbid that you'd have to find the square root of a number that's in the hundreds. So with this, if you're simplifying numbers, this is almost always the easier direction to take. First do the root, then do the power, rather than doing the power first and then the root. Keep your numbers small. So all the rules that we've had before with exponents still apply. Okay, so I'm going to cram them all on this one slide, and you probably don't really even need to take that careful of a note, because I will have this posted this afternoon. But if you remember, you multiply a to the r times a to the s, we add the 2. So the same thing here. If we have 2 to the 1/2 times 2 to the 1/3, that we just add the exponents. So it's 2 to the 1/2 plus 1/3. So make a common denominator of 6. We have 3/6 plus 2/6 equals 5/6. Okay, so we have that expression. It doesn't necessarily simplify any more than that. I mean, there's no 6th root of 2, and 2 to the 5th is 32, but that still doesn't have a 6th root. So, you know, it at least helps us consolidate different exponents. It also works for ratios. Remember, we have the difference between ratios. So if we have the square root of 2 over the cube root of 2, we just subtract the exponents, and so we get 2 to the 1/6. The exponents distribute over multiplication. So if we have ab to the r, that's the same thing as a to the r, b to the r. So if we have a term in here that has a coefficient and a variable, that's the same thing as the square root of that. It's the same thing as taking the square root of the coefficient times the square root of the variable. So here's the power to power rule where, actually I talked about this on the last slide, where you have a to the r to the s, it's just the product of the two. So if we're going to take the cube root of 2 and then take the square root of that, we can just multiply the 1/3 and the 1/2 together and we get 2 to the 1/6. So we have the 1/6 root, or the 6th root, excuse me. And just like we did with this one up here, we can also do this with ratios. So if we have a over b to the s, is going to be a to the s over b to the s. So if we're taking the square root of 2/3, that's the same as taking the square root of 2 over the square root of 3. And if we have negatives, it works exactly the same way, where negatives cause a reciprocal, right? Where if we have a to the r, a to the negative r is going to be the same thing as 1 over a to the r. If we have a to the negative 1/3, that's going to be the same as 1 over 8 to the 1/3, which then of course is 1/2. So the complicating factor here is that you have negative exponents now and you have fractional exponents. And negatives causes a reciprocal thing. The fractional exponents cause roots, okay? It's a little bit difficult sometimes to keep it straight. So, you know, it does take some practice, some careful practice to make sure you get these right. So if you're doing your homework, or we're doing a quiz, or doing, you know, some classwork or something like that, don't let go of it if it doesn't quite make sense to you. Work all the way through it, because, you know, when you have these things flying around with multiple variables and everything, you know, already with integers it's complicated. With fractions it even gets a little bit more complicated. Okay, and the last one is just an offshoot of this particular one ahead of it, where if you have already a ratio and you have a negative, you can just take the reciprocal of that ratio and keep the same exponent. So if we have 2/3 to the negative 1/2, that's the same thing as 3/2 to the 1/2, and then we can split that up, square root of 3 over the square root of 2. All right, probably time for you to try a few now. Oh, let me talk about a few tips here. I think I've incorporated most of these here. If you're going to simplify radicals, make them into exponential expressions first, because you know how to handle those. All right, when you see the square root of the cube root of 3, doesn't really pop out at you how to do it. But if you take a to the 1/3 to the 1/2, there's a path to simplifying that. Okay, so this looks like a mess originally. X to the 3rd root of x to the 6th. Well, if we convert this into exponential form, remember this will be x to the 6th to the 1/3. So we take 1/3 times 6 and we get 6 over 3. Now we can start simplifying. That 6 over 3 becomes a 2. And so we just get plain old x cubed. And you wouldn't necessarily expect that from this expression. It probably, you know, this looks like, oh my goodness, what can I do with it? It actually simplifies to something quite tidy. Okay, so here's a case now where we have the 4th root of t over the square root of t to the 5th. You simplify that first by putting in the fractional form, t to the 1/4. And then this one is going to be t to the 5th to the 1/2, so we get 5/2. And then we can subtract 1/4 and 5/2, make a common denominator, and we get t to the negative 9/2. And furthermore, we can then simplify that by getting rid of the negative by saying 1 over t to the 9/2. Everybody follow on this one? Particularly this first step, how you got from the square root of t to the 5th to t to the 5/2. Yes?
I was just wondering, as far as the answer goes, would we keep it in that form, or would we have to write 1 over the square root of t to the 9?
I would say keep it in the exponential form. I mean, you know, I'm a big fan of answering in the same form that you get the problem in, and so it is, I suppose, proper to answer it. But then you also have the rules of no radicals in the denominator, and then you're going to try and rationalize these things, and you end up with a little bit more complicated expression. Generally, when you have rational exponents and you're going to use your calculator, this is the easier way to do it anyway, because you don't necessarily have like a sixth root key on your calculator. You have an x to the y, which would be, something like t to the 1/6, that kind of thing. So the rule for simplification here is that we only have one instance of t, and the exponents are positive. It's okay that they're fractional, but we want them positive. So in this case, since we have a negative exponent, we make it positive by taking the reciprocal. Okay, so here's one, the cube root of x squared y to the 6th. And so we convert the cube root to 1/3, and now we're going to apply that 1/3 to both the 2 and the 6, and so we get x to the 2/3, y to the 6/3, and of course reduce your fractions here then, so you have x to the 2/3, y squared.
And you would just leave it as
I'd leave it like that, because if you restore that x to the 2/3, you're going back to the original expression. It's going to look like 3 times, or the cube root of x cubed times y. And so when we're simplifying these, you will get to the point where you're doing it like I guess this is a squared, not a 2, like this, which is perfectly fine. When we're simplifying it like this, that's also perfectly fine. So I guess here I'm suggesting that when you have fractional exponents and you get a simplified expression, you don't necessarily have to return it back to a fractional form. Okay? Yes, Lauren?
So on like web work, it'll want it like...
I'm not sure. I did collect up some problems for homework for tonight on web work, and I'm going to look over them to make sure that I don't set you up with a trap of it's only looking for decimal exponents or something dreadful like that, like they're looking for 0.667 or something. So I'll check that over. I'm going to try and keep it as straightforward as possible. And if I'm not satisfied that I have a good problem set, I'll assign it out of the book. Okay? Okay, so here's one. This one benefits a lot from the fact that we can split this up. We know 64 divided by 125. We normally like to simplify inside the parentheses first, right? Well, 64 is a power of 2 and 125 is a power of 5, so there's really no simplifying that we can do there. So what we'll do is we'll split this up into 64 to the 2/3 over 125 to the 2/3, and now consider the cube root before squaring it. Because if we did the squaring first, we'd be squaring 64, and we'd end up with a number well over 3,600, and then we have to take the cube root of it. Well, we know what the cube root of 64 is, and we know what the cube root of 125 is, right? It's going to be 4 and 5. And so all that remains is to square them, and so then we have 4 squared over 5 squared, or 16/25. Okay, try a few. First set is going to be all with numbers. So I want you to come up with a simplified number. Now, usually I like to see things in integer ratios, but we have a few problems. We have 2 problems that start with decimals. So these, it's fair game to end up with a decimal, although you don't have to do it that way, okay? So see what you can do here. Calculate these out, and then we'll talk about the solution. Okay, so what we want to look at is what this decimal really means. And 0.16 is 1600ths, right? So we can write it as 1600ths, and then we can take the square root of 16 and the square root of 100, and so we get 4 over 10. And so it's fair game to put it back into decimal because we started with decimal, or if you want to write 2/5, that's perfectly good in this case. Okay? All right, given that, what about the next one? The cube root of 1 over 1,000, what would that be? Yes? 1/10. Okay, so you take the cube root of 1, which is 1, so you don't even have to bother writing that, and the cube root of 1,000, which is 10. And so we have 1/10. Okay, Danielle, did you get the last one? No? Jolene, did you?
I don't know if this is right, but I got -0.002.
You're close, okay? All right, so let's look at how to do this. Let's represent this first as -8 over 1,000, right? So we can take the square root then, or the cube root of -8 over the cube root of 1,000, and so we're going to get -2 over 10, and if we want to make that into a decimal, that's -0.2. Okay, any questions on these with the numbers? Making a little bit of sense? Okay, so let's try some with actually variables in there now. So I'll give you a few minutes on this one, and the last one especially, we may get to that or we may not, but that will be the one that I start with on Wednesday, will be that particular problem. All right, so how about the next one? Okay, so first make it into a fraction, and then we can take it to x to the 3/4, y to the 2/4, and then you should be reducing your fractions. So there's nothing to do with the 3/4, but that 2/4 turns into 1/2. Okay, and then we have this next one, x to the 1/3 over x squared, and so it's going to be x to the 1/3 minus 2, and so that's going to be -6/3, which becomes -5/3, and we don't want a negative exponent, so we're going to make this 1 over x to the 5/3. Okay, so take a look at this one here, and this will be the last one that we talk about, okay? We'll do this one step at a time. We make the outer one 1/2 and the inner one 1/3, and so we get that kind of business where we have this represents the square root, this represents the cube root, and so now we just multiply the two, so we just get x to the 1/6. And so we could leave it like that, that's fine. If we want to write it as a radical, it works just fine too. We get the 6th root of x. And there again, that doesn't necessarily jump out at you from this beginning one, but you do get a really nice compact x to the 1/6 there. Now the very last one is where I'm going to start, and this one is kind of interesting in the sense that what's inside the parentheses is the same, and so we can use that and just make that 3/4 minus 1/4, which is going to be 2/4, which is 1/2, or rewrite it as even the square root of x plus y. So we'll deal with that one a little bit more in detail on Wednesday.